Okay, so now we're going to look at a bubble sort within the context of algorithm efficiency and big O notation. And let's first remind ourselves what the bubble sort does. We would use this to sort the values in an array. So for example, I have this array of gelato flavors, 10 items, and what a bubble sort would do is it would start at the top here and compare the current value of the element to the one after it. So if they're out of order, and these are alphabetically, then we would swap them. And the swapping is like a, you have this temporary variable, and I would put vanilla into here for safekeeping, and then I would move chocolate up to here, and then move the vanilla into here. It's like a three-step process. So I would go through that, through the entire array. And one pass through the array, or traversing the array one time fully, is not going to get me into perfect alphabetical order. It'll get me closer, but I'm still not going to be in order. So then I would have to loop that. So we're looping the loop. It's a nested loop algorithm. So let's continue here. Let's see here. So here's some code. And this bubble sort that I've typed out is actually not the bubble sort that is presented in your book. This is, I did this for the sake of simplifying the discussion, using the nested for loops. In your book, in the Gaddis book, they use like a do-while loop as the outer loop, and it actually is more efficient than this one. Like, the bubble sort is not an efficient algorithm, and in this discussion, you're going to see exactly why it's not. But the way I've typed this one, it's especially inefficient. So this is an absolute worst case scenario. We have these nested for loops, and basically, here's the algorithm, how it performs. But I want to focus on this area here. We have, let me just take it from the top. We have our array of flavors, which I'm calling flavors. There are the 10 items. I have the temporary variable for the swapping. And then let's say our algorithm starts here at this dash line. And so we have our nested loops. And notice that the outer loop is going to go max flavors minus 1 times. Always minus 1, because getting back to this, the algorithm is, you're always comparing like the current element to the one after it. And when you get to the end here, there is no one after it. So that's like a recipe for disaster. You would just kind of, exceed the boundaries of the array. So we always do minus 1 when we're looping through the array in a bubble sort, because as I said, you get to that last element, there is no one after it, so you don't want to go right up to the end, right up to the last element. So max flavor is minus 1. So let's keep that in mind, thinking about that. Okay. We would say that the nested loops of the bubble sort cause this algorithm to iterate n minus 1 squared times, where n is the size of the array. So max flavors is the size of the array here. It's 10. So this would go 9 times in the outer loop, 9 times in the inner loop. So that would be 81 times. So that's n minus 1 times, where n is the size of the array. Okay, so that probably makes sense. And we talked about this in the last video, though. Do we really care about that negative 1? Again, when we're talking about big O, we are interested in what happens when when the algorithm's input, and in this case the size of the array, when that input gets very, very large. So that minus 1 is not going to help if we're dealing with an array of thousands of items, for example. So what are we going to do? We're just going to throw that away, and it's not even worth mentioning that minus 1. So we would say, simplifying that, we would say in a worst case scenario, the bubble sort, or this bubble sort here, well, a bubble sort in general, will perform n squared basic steps to completely sort the array. Again, n squared, because we're just ignoring this minus 1 and we're left with the n squared. Okay, so again, in big O notation, we would say that the bubble sort's big O notation is O in the n squared, or O to n squared. And we would also call this quadratic time. In our last video, we looked at an algorithm that executed in linear time. When you have the n squared here, that's called quadratic time. Let's take a look at that in the next slide here. We're looking at the red line. Okay, this is quite different. The linear time was what we looked at in the last video. Okay, it was proportional growth, but this is exponential growth. Okay, when those inputs get very large, you're going into the stratosphere here. And so, you know, we talk about the bubble sort being not the greatest algorithm for sorting, especially if you have large amounts of data. Anything more than a few dozen items, the bubble sort should not be your go-to sorting algorithm. And this is why, because the execution time is going to grow exponentially as the input or the size of the array increases. So in the next video, we will look at the selection sort.